And here is the one that I would like to look at. So let's read the problem. It's kind of a long problem, but I think you're going to have no difficulties with it. A particle moves according to law to a law of motion, and that's given to us. Of course, time is greater than or equal to 0, where t is measured in seconds and s in feet. On page 233, problem 1. Find the velocity. No problem there. What is the velocity after 3 seconds? No problem. What is the particle at rest? We'll talk about that. When is the particle moving in the positive direction? Find the total distance traveled during the first 8 seconds. Draw a diagram. We'll talk about that. Find the acceleration at time t after 3 seconds, and then graph the position, velocity, and acceleration functions for 0 to 8. When is the particle speeding up? When it is slowing down. So it's kind of a long problem. It appears to be that way. So let's start with, I don't know, problem 2. So all these questions were problem 2. So today, okay, so this is problem 2 on page 233. We are given s of t, or f of t, as 0.01 t to the fourth minus 0.04 t to the third. And we are told, of course, t is greater than 0, t in seconds, f in feet. Okay. Find the velocity at time t. So that's part A. Find the velocity at time t. What do I have to do? Any suggestions? Yes, very good. F prime of t. Can anyone give us the derivative for this? 0.04 t to the third minus 0.12 t squared. We agree with this. So this is the velocity at time t, the first derivative of the distance formula or function. So far, so good? Questions? Okay, part B. What is the velocity after 3 seconds? How do I determine that? Velocity after 3 seconds. Very good, of course. V of 3. 0.04 times 27 minus 0.12 times 9. Whatever that is. I have my calculator. I'm lazy tonight, as you see. 0.04 times 27 minus 0.12 multiplied by 9. Correct my numbers always. So I got, so it was 327. I got 0. Is that okay? Did anyone else get 0? Yes? Perfect. Part C. When is the particle at rest? When is your car at rest? When the velocity is? Very good. Perfect. So I have 0.04 t to the third minus 0.12 t squared equals 0. I will definitely divide both sides by 0.04. And I have t cubed minus 3t squared equals 0. I can never divide by t, so I will factor. And I get 3 options, but obviously 2 of them are the same. And the third one was expected because I already got, so this is feet per second. So I get t equals 3 seconds, and t equals 0. So initially, the particle is at rest, and it happens that after 3 seconds, it's also at rest. Question so far? Okay, part D. When is the particle moving in the positive direction? Positive direction. We had situations like when the velocity was negative. And we said, well, it's not that the velocity is negative, but it just shows direction. So if a particle moves in the positive to your left, right, or up, we consider when it goes up, we consider it in the positive direction. When it comes back down, we consider negative direction. To your right, we consider positive direction. To your left, we consider negative direction. So the positive direction means the velocity is positive. In the negative direction, the velocity will be negative. So I have the velocities right here. This is the velocity. So now I have 0.04 t to the third minus 0.12 t squared greater than 0. Yes, of course I will divide by 0.04 again to clean it up. I will get t cubed minus 3t squared greater than 0. I will factor out t squared. And the question is, when is this positive? Well, this is a positive quantity. If this happens to be negative, the answer will never be positive. So obviously this is the requirement. The t minus 3 is also positive. So if t minus 3 is positive, means that on the interval 3 to infinity, the velocity is positive for t in the interval 3 to infinity. And it's negative between 0 and 3. So between second 0 and second 3 goes to your left, and ever since second 3, it will always go to your right, and it will have a positive velocity. Any questions on this idea? So it's going to your left the first 3 seconds, and then forever to your right with a positive velocity. Find the total distance traveled during the first 8 seconds. Total distance between 0 and 8 seconds. From this I know that it goes to your left between 0 and 3 and to your right after 3. So then the total distance, TD, total distance, will be the absolute value of S of 3. I should write F because we have F. F of 3 minus F of 0 plus the absolute value, which is not really needed, but F of 8 minus F of 3. Because that is supposed to be positive. Bless you. So one more time, at 0, at x equals 0, at t equals 0, between t equals 0 and t equals 3, the particle moves in the negative direction, but then between 3 and 8, it moves in the positive direction. So the distance covered will be between second 3 and second 0, and between second 8 and second 3. Why? Because I know at 3, it goes backwards. I mean, it changes direction to go into positive direction. So I have to determine these values, and I will put the function in the graphing calculator. So let's do that. In y equals, punch in, clear if you have anything else. And we have 0.01 x to the 4th, 0.01 x to the 4th, and then minus 0.04 and t to the 4th. I'm sorry, t to the 3rd actually. And now I'm checking again, yes, that's okay, that's okay, good. So we go to second and table. I have to adjust this, I'm sorry again. Okay, So go to second in table, and I need 0, 3, and 8. 0, 3, and 8. So therefore, my calculations would be the absolute value of negative 0.27 minus f of 0, which is 0, plus f of 8, which is 20.48, minus f of 3 plus 0.27. So this is 0.27 plus 20.47 plus 0.27 will be 20.75. Correct me if I'm wrong. So 5 and 1, 6, 7, and that's it. So then the total distance in feet covered by the particle between 0 and 8 seconds will be, so 2 and 1, that's 9, 0 and 1, 21. So 21.02 feet. Find the acceleration at time t after 3 seconds. Oh, I'm sorry, in F they want the following diagram. So the particle is right here at t equals 0. It goes in this direction for 3 seconds. And then 3 seconds, so this is 3. So between 0 and 8, 3, and then 5 more. So it goes to the left for 3 seconds, and then to the right. That's the diagram. Now let's look at part G. They want the acceleration now. So in G, the acceleration a of t is v prime of t, or the second derivative of the function. Can anyone give us the formula for the acceleration? 0.12 t squared minus 0.24 t. Would you agree with that? Yes? Okay, next. When is the particle speeding up and when is the particle slowing down? So let's talk about that. So we established that the particle moves to your left for 3 seconds, and then it continues forever to your right. Agreed? Okay. Now, if the particle moves to your left and the acceleration also is a negative number, so the particle moves to your left and the acceleration is also negative and pushes the particle further, then the particle is speeding up. If the particle moves to your left, which means it has a negative velocity, you know what I mean direction-wise, but the acceleration is positive, there are two forces working against each other. They're not helping one another, so the particle must be slowing down. Now, if the particle goes in the positive direction and the acceleration is also positive, again, two forces are working together, the particle is speeding up. But if the particle is moving to your right, but the acceleration is against it, which means it's negative, then these two forces are working against each other, so then the particle is slowing down. In order to establish what's happening, we will have to study the sign of both. We already studied the sign of the velocity, but now we have to study the sign of the acceleration. So first of all, I have to solve the equation a of t equals 0, like we did with the v of t. Okay, so then 0.12 t squared minus 0.24 t equals 0. Yes, of course, I will divide and clean it up by 0.12. Oops. So I have t squared minus 2t equals 0. So I'm dividing by 0.12 both sides. I factor out t, and then I have two options, t equals 0 and t equals 2. Of course, seconds. So now, the velocity, the acceleration between 0 and 8. That's what they want. One more time. Yes. When is the particle speeding up? When is it slowing down? Between 0 and 8. Going back to the velocity, I know that at 0 and 3 is 0. I know that it will be negative. It will be negative. Where did I write this? Oh, right here. That's why. Okay. So it will be, the particle has a positive velocity from 3 to infinity. So it's positive. But it has a negative velocity between 0 and 3. So now the acceleration is 0 at 0, and it's 0 at 2. And now let's look at this function and establish the sign between 0 and 2, and then between 2 and 8. I don't like to do this, but okay, let's say I plug in 1. It's a number between 0 and 2. 1 and negative. Let's plug in a number to the right-hand side of 2, like 3. 3 and positive 1. That's all I needed to establish what's happening here. So can anyone tell us what's happening between 0 and 2, between 2 and 3, and between 3 and 8? The particle is going the negative direction, but the acceleration is helping it. They're not working against each other. So it is speeding up. Now what happens between second 2 and second 3? Yes, between these two, slowing down. Good. What happens between 3 and 8? Right. Because both forces work in the same direction. It's like, for example, I ride my bike and I have a backwind, a tailwind, if you want. Then I speed up, right? But if I ride my bike and I have a headwind, of course that will slow me down. This force is against me. It does not pushing me forward. It's the same idea. They also want us to graph all three with a graphing calculator, so let's do that. So in y equals, this was the function. So the velocity will be, one more time, 0.04 tx to the third, and then minus 0.12 x squared. And then the acceleration would be, what would be? 0.12 x squared, and then minus 0.24 x. So careful, they're coming now quickly. So I'm going to press graph. Let me use the Zoom 6 standard. And here it is. So here is, as expected, the distance, the derivative of this. Of course, this is negative, right? Here's the derivative. And here's the acceleration. I want to change the viewing window. For a second, I forgot that we're talking about time. I don't care for the negative side. So this is the distance. So here is the velocity. And here comes the acceleration. Okay, I'm going to change the viewing window again. I don't care for too much negative on the y-axis. Okay. Distance, acceleration, I'm sorry, velocity, and then acceleration. I am going to remove for a second the distance formula, and I'm going to adjust the viewing window for the y only between -2 and 4. Here's the velocity. Here's the acceleration. Notice that between 0 and 2 seconds, they're both under the x-axis. They're both negative. So the particle is speeding up. Notice that between 2 and 3, the acceleration is positive, but the velocity is negative. So that's why the particle between second 2 and second 3 is slowing down. However, now they're helping one another from 3 to infinity. Both are on the above the x-axis, so the particle is speeding up. Questions on this problem? Questions. Exactly what we got from studying the sign of the velocity and of the acceleration on the same 0 to 8. Questions? Everything okay? Okay. So let's talk a little bit about what is left from this chapter, because I would like us to think about test 2 already. Of course, we'll have a full review of the one session. So let me just tell you what is left. So 3.9, related rates. This is a major topic. I need the entire semester for this one alone. So we're going to work on as many problems as possible for a session or a session and a half. We'll see. Then 3.10, extremely important. It's called differentials. And approximations. Another very important topic. And 3.11, we're going to talk about hyperbolic functions. Only 3 of those, and their derivatives. And you can say, really? Don't we have enough functions? Inverse trig, exponential, log, polynomial, rational, radical, absolute value. Isn't that enough? No. These functions are based on the exponential function. They're combinations of the exponential function, and I'll show you applications of that. So let's get started on related rates. First of all, just those 2 words put together. What does that mean? Related rates. For example, imagine we have a balloon and we pump air, or a tire, and we pump air in the tire or in the balloon. What happens? A lot of things happen. The volume of air increases. The radius of the balloon increases. The surface area expands. A lot of things happen at the same time. So they are related. What do you mean by rates? The rate of change of the radius with respect to time, the rate of change of the surface area with respect to time, the rate of change of the volume with respect to time. They're all related. One triggers the other. Or somehow, because they happen at the same time, they are related. So we have tons of examples here of all sorts from everything. We do not cover 3.8. I hope you noticed. 3.8 is not part of this course. It's part of the previous course, the pre-calculus. Okay, so let's start with an example. Let's start with a simple one. Let's read it. Okay, simple one before we go into more complicated situations. The radius of a sphere is increasing at a rate of 4 millimeters per second. How fast is the volume increasing when its diameter is 80 millimeters? So this is problem 6 on page 248. So 3.9, 6 on 248. So every time we read a word problem, we should read it at least twice, in my opinion, and take notes. So I am given 4 millimeters per second. How fast is the volume increasing when the diameter is 80 millimeters? First of all, let me give you the volume of this sphere. 4 pi divided by 3 r cubed. It's for sphere. The volume of the sphere is 4 pi over 3 r cubed.
Are you going to give us like the formula?
Oh, we have to remember the volume of a sphere and the volume of a cone and the volume of a cube moving forward. Okay. So first of all, the question I have to myself is, what is this? Excellent. The rate of change of radius with respect to time, that is given to us. Excellent. Now we're asked to find the rate of change of volume with respect to time when the diameter, which is twice the radius, equals 80 millimeters. Do not erase anything, I'm just making a point. All this information is for later. Cannot be used at this point. Because I cannot plug in something if I don't have the function. So I have to find the function first, I have to differentiate it, and then I plug in whatever. So please do not ever get confused with this and start with it. Okay, so we're asked to find the rate of change of volume with respect to time when, and that has to wait. So what do I have to write? What do I have to do? What do I have to determine? I have the function. But what do I have to find now? As you've noticed, the radius is a function of time. The volume is a function of time. So what am I really asked to find? That's my first question. That's it. dv over dt, and now I can write, if you want, when the radius is 40 millimeters. This is what I'm asked to find. But first, I have to determine this. There is no question that this has to wait. I have the formula, I have the function, so let's differentiate dv over dt, keeping in mind that this is a function of time as well as this. Because when we pump air in the sphere, the radius changes with time, so it's a function of time, and the volume changes with time, so it's a function of time. So how will you differentiate this? Keeping in mind that r is also a function. Yes? dv dr over dt. Excellent. 4 pi r squared dr over dt. Do we understand this? Do we have any questions on it? Is this okay, everyone? Now I have the formula, I have the function, I have the derivative. So then when r equals 40 millimeters, I have no problem with 4 pi 40 squared dr over dt times 4. And you will give me the measurement unit in a second. So this is 16, right? 16 times 1600. I got 25600. Of course, pi, because I did not include that. Measurement unit. The measurement unit of the top over the measurement unit of the bottom. What is the measurement unit for the top? It's not the area.
So,
Yes, millimeters cubed per second. Remember, every rate of change has two measurement units, one coming from the top and one coming from the denominator. So if you ask me what is my speed, I'm not going to say 40 miles. It's a rate of change of distance with respect to time, so I have to say correctly 40 miles an hour. Any questions on this? So what did we understand or learn from this is that the volume and the radius, and yes, the volume of the sphere and the radius of the sphere change with time. They are both functions of time. And their rates are related. How? Here's the relationship. 1 equals 4 pi r squared times the other. That's the relationship between the two rates. They are related, and this is the equation that relates them. Any questions on this problem? Okay, moving on. Let's continue with something else. Yes, let's look at this. 15. Two cars start moving from the same point. One travels south at 60 miles an hour and the other travels west at 25 miles an hour. At what rate is the distance between the cars increasing 2 hours later? Whatever comes after when, you have to disregard till the very end. Two cars start moving from the same point. One travels south at 60 miles an hour and the other at 25 miles an hour going west. So south and west. At what rate is the distance between them increasing 2 hours later? So that is problem 15 on 248. $60 miles per hour, 25 miles per hour. And we want to determine the rate of change of this. And I cannot write dd, so I have to write w. So one goes south, they say, one more time at 60 miles an hour, and the other one west at 25. So we want to find what? What are we asked to determine? dw over dt, this is indeed the question. Very good. When t equals 2 hours. But this has to wait. Perfect. So anyone has any idea how to proceed? What do we need to do? Any suggestions? I gave you the hint. It's right there. The Pythagorean theorem. X squared plus y squared equals w squared. Okay. Now, let's establish what this is, and let's establish what this is. What are we given in this problem? We're given at 25 miles an hour, we're given at 60 miles an hour. What do they represent? This one represents, of course, thank you very much, dx over dt. What does this represent? Very good. What do you think we're going to do here? Here's your hint. Of course. So can anyone give us the derivative on the left? Keeping in mind that x and y and w are all functions of time. Very good. So please tell me what to write on the left. Very good. Plus 2y dy over dt equals 2w dw over dt. Notice that this is exactly what we are after. But of course, after I divide both sides by 2 and by w. So I have x dw over dt equals x dx over dt plus y dy over dt, everything over w. I determine the derivative of w with respect to time. Now, I can continue evaluating it when t equals 2 hours. But I'm far from being done with this. This I have. How much is this? Excellent. How much is this? Perfect. This I don't have, but I can take it from here by taking the square root. So this piece is the square root of x squared plus y squared in a moment. But now the question is, how do I get this and how do I get this? Because otherwise I won't be able to solve or get a number. But what does x represent? Is the distance covered by the car driving at 25 miles an hour. What does y represent? Is the distance covered by the car driving at 60 miles an hour. And now we do have the time of 2 hours. So how do I determine x? X will be, when time is 2 hours, 2 times. Very good. And when time is 2 hours, y will be 120. So this is 50 squared and this is 120 squared. So now I have all the numbers. Let's nicely put them together and then find the answer. So dw over dt, when the time is 2 hours, we get 50 times 25 plus 120 times 60 over the square root of 50 squared plus 120 squared. I don't recommend doing anything piece by piece. I recommend putting in everything in the graphing calculator, but you have to be very careful with parentheses around the numerator. So parentheses, 50 times 25 plus 120 times 60, close the parenthesis, and then we divide by the square root of, you know me, I have to have parentheses, 50 squared plus 120 squared, and close the parenthesis. And now I press enter, and I get 65. Doesn't mean anything without the measurement unit. 65 what? It depends on what dw over dt represents. Of course. Thank you. 65 miles an hour. Any questions? Any questions? Okay, so let's look at another. They're all, almost all of them are different. Yes, let's look at the conveyor belt and the cone. So we have gravel being dumped from a conveyor belt at a rate of 30 cubic feet per minute. What does this represent? 30 cubic feet per minute. dV over dt, well done. And here it is. So it forms a pile, and there is a condition here that the diameter and the height are always identical. It says base diameter and height are always equal. So this is not something that follows when blah, blah, blah. This has to be taken into account from the very beginning. Now the rest you have to disregard till the end. How fast is the height of the pile increasing? When? So that's after when, you have to forget about it. when blah, blah, blah. So we know that the base diameter and the height are always the same. That's given, and it has to be clear. dV over dt is given as 30 cubic feet per minute. How fast is the height of the pile increasing? Blah, blah, blah. So, ready? So this problem is 27 on 249. So we have this situation. So this is the diameter. This is the height. And the height and the diameter are always the same throughout this process. We are given dV over dt as 30, and it was indeed in cubic feet, yes. I'm just making sure, per minute. We're asked one more time to find how fast is the height of the pile increasing when the pile is 10 feet high. So what are we asked to determine here? Excellent. The age over dt when age equals 10 feet. But this has to be disregarded till the very end. We cannot plug it in before we have the function and we have the derivative. And we will plug it in the derivative. Question so far? Where is the starting point? So let me refresh your memory. We know the volume of a sphere. Here's the volume of a cylinder. And you say a cylinder? Yes, just bear with me. Area of the base, which is pi r squared times the height. The volume of a cone is identical, but divided by 3. That's why I wanted you to remember this. So once you remember the volume of a cylinder, area of the base, which is pi r squared times the height, you should never forget the volume of a cone. So the volume of a cone is the same thing divided by 3. So area of the base times the height, but this time for the cone divided by 3. Okay, perfect. So where is our starting point? What do you think? So first of all, I do not... Okay, so we want to substitute. First of all, we cannot really use the radius. I don't care for it. I don't know anything about it. And I am really asked to find this. So I want this to go away. Well, I can't erase it, but I can do something about it, right? Because the height equals the diameter, or 2 times r. From this relationship, I can solve that equation for r in terms of h, right? So h equals 2r. So then r equals h over 2. And this is what I have. That's where my starting point is. The radius in the volume of the cone has to come out, has to be replaced by h squared over 4. So then the volume of the cone for our situation is pi over 3 times h over 2, everything squared, replacing r by h over 2. And then I copy h. Any questions so far? Is this okay? Are you with me? So then I square, and I simplify a little bit. So let's look at the volume of the cone. Equals pi over 3 times h squared over 4 and times h. So this is pi divided by 12 times h cubed. Questions? Okay, now we're ready. We're ready for what? Yes, so we differentiate. So let me write it one more time. We differentiate the left and we differentiate the right. But we have to keep in mind one thing, that v is a volume and it depends on time. It's a function. And h is height. It depends on time. It's a function. So the left-hand side is, that's it, dv over dt. The right-hand side is pi divided by 4 r, h squared times dh over dt. Be very careful how we solve for dh over dt. Is this piece over this piece. So dh over dt equals, at the top, dv over dt, we cannot separate that, those two, divided by pi over 4 times h squared. Nobody cares to simplify this. Now we're ready to plug in 10. So for h equals 10 feet. The top was given to us as being 30. Then we have the pi over 4 that we have to copy, and we multiply by 100. Before I put in the graphing calculator, I recommend you simplify a little bit and flip pi over 4 into 4 over pi. So this is 12 over 10 pi. And you can simplify it by 2 or not. Let's approximate it. So careful, it's 12 and it's divided by 10 times pi. So I got 0.38 approximately. So what does this represent? It's a rate of change. It has to have two measurement units. Feet per minute. Very good. Because it's the height. The rate of change of height with respect to time, indeed,